Welcome to the second week in April. This should be April 7th, and we're talking about Chapter 33, Electromagnetic Waves, today. I know, we skipped Chapter 32, and I don't think we'll be missing too much of material there. But anyway, I did want to mention to you, in case you had not seen their earlier information, that the homework assignment for this Chapter 33 will be the problems at the end of the chapter, numbers 4, 6, 12, 24, 33, 47, and 58. I should put those into an email or something that I send to each of you so that you have that at another source as well. But it is 7 problems, and those are due on Thursday before the beginning of class. Submitted the same way we did the ones before. Now, electromagnetic waves. Well, as far back as Maxwell's time in the mid-1800s, we knew not only about the visible spectrum, but we knew also about the infrared and ultraviolet forms of light that made up part of the electromagnetic waves. Since that time, we've expanded that way beyond that to where we have radio waves, which and X-rays and gamma rays. X-rays actually came about in the late 1800s with the radio waves and the gamma rays being utilized very early in the 20th century. So that is the whole spectrum of it. And of course it goes from red to orange, yellow, green, blue to violet. And as you go to larger wavelengths, you're going to smaller frequencies. When you're going to smaller wavelengths, you are going to higher frequencies. Now, electromagnetic waves are generated in the following manner. You have an energy source that feeds it into a circuit with a capacitor and an inducer and an LC oscillator. It is coupled with a transformer, and then the transmission line takes it to an electric dipole antenna, and from this point, waves are generated, and they are, even though this is flat, they generate out from there and sort of a radius, a spherical sort of or conic type of distribution, and are detected at some point P distant from that source. So the electromagnetic wave is shown over here. And you can see that at every point you've got an electric field and the magnetic field induced by it, or the magnetic field and the electric field induced by it. But be that as it may, they're always perpendicular to each other. And therefore the wave is traveling transverse to them, and it is in the direction of the cross product of those two vectors. The fields are always sinusoidally in variation, and they vary with the same frequency, are in phase with each other, and to those you can actually add signals, and we'll talk about that later. So in keeping with these features, it's possible to deduct that an electromagnetic wave traveling along an x-axis has an electric field E and a magnetic field B with the magnitudes that depend upon how far it has gone on that axis and the time it takes to get to that point. And if it's of this form right here, E equals EM sine kx minus omega t. EM and BM are the amplitudes of E and B respectively. And the electric field induces the magnetic field, as I mentioned, and vice versa. Now, wave speed, we remember that the wave speed, and it's missing here. The wave speed is actually omega over k, right? Remember back from chapter 16 when we had the wave speed as nu equals omega over k. However, because this is an electromagnetic wave, its speed in a vacuum is given by c rather than v. And so c has a value given by, and we're missing that as well. And it equals 1 over the square root of mu 0 epsilon 0, where mu 0 is the permeability constant and epsilon 0 is the permittivity constant. So C equals 1 over the square root of mu 0 E0. I believe that's equation 33-3 on page 975. So, in other words, all electromagnetic waves, including visible light, have the same speed c in a vacuum. Okay, let's go to the first practical exercise. Project Seafarer was an ambitious program to construct an enormous antenna. And this right here is problem number 2 at the end of the chapter, by the way. It was buried underground on a site 10,000 kilometers square in area. Its purpose was to transmit signals to submarines when they were deeply submerged. If the effective wavelength were 1 times 10 to the 4th times the Earth radii, what would be the frequency of the radiations emitted? And what would be the period of the radiations emitted? And ordinarily, electromagnetic radiations do not penetrate very far into the conductors, such as seawater. So normal signals cannot reach submarines, and that's the reason why they had to have this type of a system. So anyway, my camera did not come in, so I'm just going to walk you through these. And there have been some, again, glitches that I can't correct on these slides, but we'll just work through them. Now, first of all, lambda equals 1.0 times 10 to the 4th times the Earth radius. And the radius of the Earth is 6.4 times 10 to the 6th meters, right? You get that from the back of your book. And so their frequency then equals the speed of light divided by lambda. And so lambda is going to be that 1.0 times 10 to the 5th times the radius of the Earth. And this right here is the speed of light. That works out to, that's actually 0.468 times 10 to the minus 2nd hertz, or to give it to the correct significant figures, is 4.7 times 10 to the minus 3rd hertz. So they did get that one right. The period of radiation is just the inverse of that. So you take 1, and I actually did it so that I used the earlier numbers, and that would give me essentially 214 seconds, right? If you did that, so it's 214 seconds, not the number that they have here. If you carry it out to the correct number, to the if you don't do your rounding until after you've done your calculations here. It works out to be actually 3.57 minutes. Okay, now the next one. Approximate the smaller and the larger wavelength at which the eye of a standard observer has half the eye's maximum sensitivity. What are the wavelength, frequency, and period of the light where the eye is most sensitive? Well, okay, you just have to interpret the graph here. And it doesn't show it here, but this goes all the way from 400 here to at 50%. This line right here is 500. This line out here is 600, and this one right here is 650. Okay. Maybe I can get that down just a little bit more so that we can bring that down. I would like you to be able to see that. So what we have here is that the 50% right here would be at this point. And when I looked at that, I had that as 515 about. Okay. Going to the larger one over here, I had that at about 610. Okay. 1/5 of the distance between these two. Then when I went to the maximum, it's just a little bit above the 550. And so I gave that about a 555 value for the wavelength. All of these wavelengths here are in nanometers. Okay, so that's the larger and the smaller. So the wavelength and frequency in the period where it's most sensitive, for well, as I mentioned, part C then, it is going to be at 555 nanometers. And since frequency equals C over L, that's going to be 3.0 times 10 to the 8th nanometers per second divided by 555 times 10 to the minus 9th meters. I calculated that out as 5.41 times 10 to the 4th hertz. And then the period is just going to be the inverse of that. Yes, they did get their numbers agreed fairly well, quite well with the ones that as my eyes saw on there. And as I mentioned, the period is just the inverse of that, and so that is 1 over f, or 1.85 times 10 to the minus 15th seconds. Now, we have to adjust this again just a little bit. The energy transport and the Poynting vector. Okay, this is POY. It's named for a fellow by the name of Poynting, not not the usual type of thing where you have your finger stuck out. The Poynting vector is the rate at which the unit area is the rate per unit area at which energy is transported via electromagnetic wave. Okay, and it's given by this vector right here, the cross product of these two divided by this permeability coefficient. So that is called S. Okay, and with a vector. So this is the direction of an electromagnetic wave at any point, and it gives the direction of travel and the direction of the energy transport at that point. Okay, and so this is your S value here, radius, it's out in this direction right here, and the energy emitted by the light source S. So here is S is the source. This is not the same as this right here. This is the vector. This S here only stands for source. Okay. Again, I don't know how they why they want to confuse you that way, but they do. Let's move this down just a little bit so we can get the rest of this in here. The time average rate per unit area at which energy is transported is S average, which is called the intensity of the wave. This is a critical equation right here. Intensity equals 1 over C mu 0 E root mean square squared. So this right here is this the magnitude of EM divided by the square root of 2. Okay, and so this right here is squared, and so this is the EM squared divided by 2 is what goes into this equation right here. So a point source of electromagnetic waves emits waves isotopically. In other words, equal intensity in all directions. That's what isotopically means. The intensity of the waves at a distance r away from there, from a point source, where you've got a power here for the source, is the power divided by the area. That's the power of the source divided by 4 pi r squared, which is the distance out there. Okay? So let's continue on. Move this back up a bit. And we get to checkpoint 2. There actually was no checkpoint 1. The figure here gives the electric field of an electromagnetic wave at a certain point and a certain instant. The wave is transporting energy in a negative z direction. Okay, this is the negative z. In what direction of the magnetic field of the wave? What is the direction of the magnetic field at this point and instance? And if you think about that, you will come up with that it is the positive x direction. The positive x direction. Okay? So anyway, we will stop there and begin with the next one after this particular section.